So it's time we look into the history of the atom. When we're trying to figure out what made the world go round and what made matter consist like matter, in 1807, Dalton came up with what he termed his atomic theory. He specifically said that matter is made of atoms, and those atoms are the smallest unit of any element that retains its properties. Elements consist of only one type of atom, and each of these atoms are identical. Okay, so that may not be totally completely correct, but you know what? It's somewhat close. So elements will differ from one type to another type. So if you have an element, basically it's kind of like others of its own kind, but not like another kind of element. These things didn't seem like they were, may not seem radical now, but they certainly were back then. Compounds are made with atoms of two or more elements combined in small whole ratios. And finally, Dalton said that atoms were not created or destroyed, but undergo chemical changes to form new compounds or molecules. So we actually refer to that last little bit here as the law of conservation of matter, which we talked about in lesson 1. So as time moved on, a guy named Proust, he's a French chemist, came up with the law of definite proportions, or the law of constant composition. And what that said is that all samples of a pure compound contain the same elements in the same proportion by mass. So in other words, when you have water, it seems like there is about 2 grams of hydrogen for every 16 grams of oxygen. That gave a ratio and allowed Dalton and some others to kind of figure out some more information here. That led to the law of multiple proportions. So basically what this said is that when 2 elements react to form more than one compound or to combine to a compound, the mass of one element that combines with a fixed mass of the other are a ratio of small whole numbers. So here's the important part here. You've got a ratio of small whole numbers, and that's what makes the new compound. So if you start with carbon and oxygen, they can form CO2, and that would be a mass of about 44. Or you can form carbon monoxide, or CO, which has a mass of about 28. And those are consistent, okay? So we understand that ratios and masses relate to one another. So in other words, if I have a mass that's consistent, I can think of how those atoms can form ratios with one another to give us a compound formula. And finally, J.J. Thomson came in with what's known as a cathode ray tube. Now what this is, I'm sorry y'all, I can't draw worth anything, but what this is it's like a sealed glass tube, and it's been vacuumed out of all of its material. So there's not really mass inside there. The chemicals are gone, air is gone, and this tube is really good for passing through cathode rays, which really end up being electrons. So J.J. Thomson ran positive and negative magnets by the tube and measured how that beam of electrons right there bent. And what he found is that the beam bent toward positively charged magnets and away from negatively charged magnets. Well, the reason why is because it was an electron, and this allowed Thomson to calculate the charge and the relative mass of what we now know as an electron. Okay, as time progressed, more information was known. Millikan in 1909 came along and he made an oil droplet experiment. So what he kind of did is he sprayed sort of like what's a perfume bottle into this tube of something that he can look at. And he suspended these tiny oil droplets by using charged plates. And what that actually ended up determining was the charge of an electron. Combined with Thomson's work, they could actually really determine the tiny, tiny mass of an electron in much better detail. So what we found out by this time is that an atom could divide, like it was divisible. You could take parts of it away from each other. So what does this atom look like? We still didn't really have a model for what atoms look like. So several different atomic models were proposed. Things that look like plum pudding, where maybe protons and neutrons were spread throughout the entire atom. Those things were proposed. And it also, maybe some other types of models look sort of like Saturn. We just really didn't understand things. And along came my favorite experiment, and that is that of Ernest Rutherford. What he did is he took alpha particles right here. So alpha particles, and these are kind of like tiny, tiny, tiny particles, sort of like what a nucleus would look like. And he started shooting those particles at a piece of gold foil. And what he found is that, yeah, most everything went straight through to the other side. But every once in a while, one shot off to the side, suggesting that it hit something that was a really hard center. And that is where we figured out that atoms have a nucleus. And that's very, very important to understand, right? So this is what allowed us to sort of understand what an atom looked like. There were additional types of research that were made. Soddy used radioactive decay to identify that we could have different isotopes. And what an isotope means is that you've got different numbers of neutrons within a mass. But it really didn't change the properties or reactivity of a chemical or an element very much to change the number of neutrons that were present. That's actually really important as well. In 1932, Chadwick finally found these evidence of the neutrons that, by the way, were those. We didn't really know that they existed, we thought they did. So now we have protons, electrons, and neutrons, and we understand that at the center of an atom, you have a nucleus, and that's where your protons and neutrons exist. Electrons circle that nucleus center, so they're the ones that are on the outside there. But in truth, all this stuff that's in the middle is just empty space. And as a matter of fact, if you were to draw this to scale, that dot might be right there, and the actual electrons are probably way off the page and maybe outside the building even that you are currently in. Because most of everything is actually empty space. And that might be really weird, but it's completely true. So that's an interesting fact that we'll come back to and talk about later too. But let's simplify things. Let's talk about what charges we have and the relative mass we have of all of our subatomic particles now, okay? So a proton, we're going to say, has approximately a +1 charge. And we made this new unit called atomic mass unit just to basically put everybody on the same playing field. We'll talk about what that means later. But the mass of a proton is about 1, and he lives inside the nucleus. Okay? Then we have neutrons. Neutrons have no charge. That's why they're called neutrons, because they're neutral. They have a +1 mass, and they also live in the nucleus. And finally, you have electrons. Electrons have a -1 charge, and check this out. Relative to a proton and neutron, they have like no mass. It's not that they really have no mass, it's just that it's so teeny tiny. It's like 1/1/1800th of that of a proton or neutron. And these guys exist on the outside. So that's that blue line that you see over there. Okay? So when it comes to the periodic table and looking at how symbols appear in chemistry, there's different ways that we represent things. I think it's kind of funny that when we represent most of our symbols in chemistry, it kind of looks like the periodic table, but it's backwards. And here's what I mean by that. If you see something that's like this, that's K. First of all, what that tells you is it's the atomic symbol. It tells you what the element is, okay? So this is standing for potassium. The number up top tells you the mass of this particular element that it's talking about, this particular atom. And down below is the atomic number. The atomic number is also equal to the number of protons in potassium. It'll also be equal to the number of electrons if the atom is neutral. But in this case, it's not, because we see up here, there's a positive charge up there, okay? So you can't get that confused with what things look like in the periodic table like this. There's a difference right here. See how that number is not just 39? That's actually an average of all the different types of isotopes that exist out there, period. So it's not going to be as simple of a number that you see, but also that 39 that exists on the periodic table is going to be the opposite. It's going to be on the bottom rather than on top, okay? So by these values, though, we can tell in the atomic symbol what our atomic number is, because that represents the number of protons. That's what actually defines which element we're talking about. The atomic mass is equal to the number of protons plus the number of neutrons. So in this case, we could take that 39, subtract the 19 protons, and you get 20 neutrons. Let me explain that a different way. If your total mass is 39 and 19 of that mass is due to protons, that means that 20 of the mass has to be from neutrons, because remember, most of the mass of the molecule really comes from protons and neutrons. And finally, we have the atomic charge. Now, this is where a lot of people get confused, because electrons are negative. So if you lose an electron or you subtract an electron, that's how you end up with a positive charge. So I've set up this equation here to state that if we have 19 protons, I would then subtract the number of electrons to give me that +1 charge. So if I have 19 protons, I would only subtract 18 electrons in order to give me that +1 charge. And so this element would only have 18 electrons. Okay. Here's another example really quick. If you have fluorine with a -1 charge, here is our atomic mass, here is our atomic number. That would mean that there are 9 protons, as we see in the atomic number. 19 minus 9 gives us the number of neutrons. And in this case, we're going to have more electrons than protons, because we would subtract more electrons to give us a negative number. So yes, it's weird. You have to add electrons to get to a negative charge, or you have to subtract electrons to get to a positive charge. Okay, I sort of already talked about this. When we get to the bottom number on that periodic table, this 39.08 here, right? What that is saying The reason why it's not a simple 39 is because it is indeed the average of all the different neutrons of that same element in the universe. That's pretty cool when you think about that. So we can calculate that because it's the sum of the abundance of each kind of isotope that exists times the mass of that isotope. So here's what I mean. So here's an example problem. Let's say that we have chlorine 35. This has a mass given right here in AMUs, and that's how often that particular chlorine exists. Another form of chlorine has this mass and this abundance. Well, what we first need to consider is that these percentages together would add together to 100%. Percentages are really something that represents the whole of something that exists. Well, we have one universe. So you need to take those percentages, divide them by 100, so that they will together add up to 1 and not 100%, because we need them out of percents, okay? So divide each of those numbers by 100, and that will give you the relative abundance within the one whole universe. So those two things would add up to 1, okay? Now we just multiply the masses by their abundance. So this number right here comes down, and see how that had to do with the 75? I multiply them and add that to the 36 times 0.24, okay? Multiply these together, and then add those two values together in order to get your correct sig figs, right? And that will give you a total of 35.46 AMUs. Please do try to practice this as well.